Hello, this is Rachel Babin from Oncology News Australia, proud producers of the Oncology podcast. Welcome to another fantastic edition of the Oncology Journal Club. This week, Eva Segelov talks us through proton beam therapy, and Craig Underhill reviews papers that bring new standards of care in lung cancer from the recent World Lung Cancer Conference. Hans Prenen chats about nanotech with our guest interviewee this week, Associate Professor Giovanni Maglia, who is an expert in electrophysiology and single-molecule nanopore technology at the University of Gronginen in the Netherlands. Hans's quick bites include an update on the Cytosponge and a thought-provoking study on industry payments to Australian medical oncologists and haematologists. We hope you enjoy today's entertaining and informative episode. As ever, links to all of the papers discussed today are available in the notes. For the latest oncology news and podcast updates, subscribe to the Oncology newsletter. You'll see a link on oncologynews.com.au. This is Rachel Babin, and this is the Oncology podcast.
Good day, good day, good day.
G'day, g'day. Get off. G'day. It's the Oncology podcast. Actually, the Oncology Journal Club podcast. You've put me off now, Hans. We're back for another fantastic episode of papers, banter, fun, and a bit of serious stuff all about what's going on in the cancer world. So hello to you over in Belgium, Hans.
Hi, Eva. How are you doing?
I'm doing great. What about Craig?
G'day, everybody. Hojen Dag, Hans.
Hello, Craig.
You can nearly do the whole episode in Flemish now, Craig. Well done. So today we have a real mixed bag for you. We've got some interesting and quirky papers. We've got a fantastic interview looking at cutting-edge technologies that are coming through for cancer therapy and the magic nano word. So Hans has rung up the CEO where he's got all his funds invested and asked for an interview in that company. Is that right, Hans?
That's completely right, Eva.
Okay, good. So you'll get some stock advice as well, perhaps.
That's what I hope.
Good-o. So I'm going to kick off with a paper, and I'll tell you why I've chosen it. It's a randomized phase 2B trial of proton beam therapy versus intensity modulated radiation therapy, IMRT, for locally advanced esophageal cancer. It's a paper out of MD Anderson, published recently in JCO with an accompanying editorial. So why have I chosen this? Because proton beam is coming to Australia and we don't know a lot about it. Speak for yourself. You missed your cue, Craig.
I'm just online shopping. Sorry, Eva.
Proton beam 101 is that the physical properties of a proton beam allow energy to be deposited at a specific depth with very rapid energy fall off behind it. So it's got the potential really to reduce the dose to normal tissue and much more safely deliver therapy to treatments close to critical organs or where you want dose escalation using trimodality therapy, where you're re-irradiating a region, or in elderly patients. So for all those reasons, it's particularly suitable for esophageal cancer. Now, retrospective series looking at outcomes from proton beam all suffer from the bias of the patient selection for people who were treated. And there's very little randomized data, and that's actually limited the uniform acceptance of proton beam, except for 3 categories where it's pretty standard: pediatric malignancies, ocular tumours, and chordomas. It's actually been 32 years since it was FDA approved. Of course, we equate it with very high cost, but even that cost is coming down. And proton beam has actually been shown to be cost effective for certain cancers, including locally advanced esophageal cancer, because it reduces the morbidity associated with the alternative treatment and the mortality. So we know that IMRT has really largely replaced 3D conformal radiation, even though that happened with very little randomized data across treatment sites. In fact, only 6% of NCCN recommendations for IMRT are based on level 1 evidence. Now, here's a fact you won't know, Craig. What is the units of dose for proton therapy?
Oh, no, I have no idea, Eva. I don't even know about normal radiotherapy, so tell us.
Well, I'm sure you've heard of Gray.
Oh, yes. Yep.
The dose here is given in units of CGE, and that means the dose in Gray multiplied by a relative biologic effectiveness factor. So true proton versus photon randomized trials have really only just started being reported. There are some trials in non-small cell lung cancer with concurrent chemotherapy, but lots of flaws in the design. And some trials showed no significant difference between the two arms, but there really was a learning curve associated with giving proton beam. So this was a randomized trial looking at patients with locally advanced esophageal cancer. They got 50.4 Gray of IMRT, or the equivalent of proton beam therapy. They included ECOG2 patients because it's actually in the poor performance status that this technology maybe give us the most benefit. And they included esophageal cancers of all locations and histologies. Now, they made up a new primary endpoint called TTB. This was a composite score of 11 distinct adverse events. They included common toxicities, but also post-operative complications for patients who proceeded to get operations. And they tried to quantify the severity of the AE experienced over the duration of 1 year following treatment. So an interesting endpoint, although not validated. And the other pre-specified co-primary endpoint was PFS. This study started in April 2012. That's how long ago these trials started. And the results were actually the trial closed early because they activated another study that they thought was superior and had overall survival as an endpoint. There were 145 patients randomly assigned, but only 107 patients were evaluable. That's a common problem with these trials. Median follow-up, 44 months. So we had 51 patients who proceeded to esophagectomy. In the end, there was no difference between the 3-year PFS at around 51% in both arms and 3-year OS around 44.5%. The post-operative hospital stay was lower for the mean but not the median for the proton group. The quality of life was said to be the same, but this composite score of the distinct adverse events was significantly better for proton beam. So the conclusion and the accompanying editorial talked about how significant this was as a randomized trial comparing these therapies. It discussed the limitation. A lot of patients who went on were not able to receive the proton beam because the health insurance in the US wouldn't pay the costs. It was single center, and it did use an old technology of proton beam because they now have intensity modulated proton beam therapy. We are getting a proton beam facility in Adelaide, and it will be interesting to see that technology rolled out beyond the traditional use to some of our older and frailer patients. Hans, do you have proton beam in Belgium?
Actually, we do, and I find it a very interesting topic because, as I explained in previous podcasts, we have a Flemish region, we have a French region in Belgium, we have a small German. And the main problem is actually you only need one proton center per, let's say, 20 million people. So in Belgium, I think one center would be enough. But of course, you have different populations, so we have two. My question to you, Eva, so you're speaking about Adelaide. Is the plan to have only one in the whole of Australia? And then a lot of people have to travel quite far to get there, no?
So the funding, as I understand it, is for one centre. It was pretty hotly debated where to put that centre. But again, that was thinking about these sort of rare special categories of patients. I think these trials are now showing that this should perhaps move more into mainstream. And wouldn't we love a less toxic technique for patients, particularly poor performance status with locally advanced esophageal cancer? We see a lot of morbidity.
I think that's completely true, but there's still a debate about the cost effectiveness of these centers. The cost to place it is huge, and then you still have a high cost to keep it going. But I'm very pleased that there are now trials that show the benefit, because if there are no trials to show benefit, we should not invest in this technology, of course.
Although they do make the point IMRT was taken up to be standard with very few trials, and obviously that's because it's a lot easier to implement.
True.
So I'm going to be provocative, Eva, and say, do you really think this is going to have as much impact as if we can get standard radiotherapy access to all of the underserved populations in Australia, as opposed to a super specialised centre for a few patients in terms of proton beam? So that's possibly an interesting question we could debate another day.
Well, it comes back to that, should we put all our money into stopping smoking and not treat anyone with advanced lung cancer? Of course, you would be better to have many facilities delivering standard and optimal therapy, but human nature, we progress on multiple different levels. So
sure,
we're flying to the moon in the middle of the COVID crisis in the US. It's a funny paradox, isn't it?
Yeah.
So I gather you're not going to talk about proton beam, Craig. You are going to talk about standard therapy that was discussed and the new wave of standard therapy at the recent World Lung Cancer Conference virtual. How did it go?
Yeah, well, that's right. I'm going to actually talk about possibly some new standards of care in the lung cancer space. So these were presented. I've got 3 abstracts, papers to present. So the International Society for Lung Cancer World Lung Cancer Conference was meant to be recently in Singapore, but because of COVID, it was delayed till, I think they're planning to do it in February, but, good luck with going ahead with that, flying people from around the world to Singapore for a long weekend. So what they did instead was had a virtual presidential symposium, they called it, and they had 3 educational talks, and then they presented 3 randomized phase 3 studies, which, as I said, may influence the standard of care.
So, Craig, this sounds like you'll take a while. I'll just nip over and do some online shopping.
Yeah, thanks, Eva. So the first paper was called Orient 11. So that was a randomized trial done in locally advanced or metastatic non-squamous non-small cell lung cancer, and it was comparing platinum pemetrexed doublet with the addition or not of sintilimab, which is a PD-1 inhibitor developed by a Chinese pharmaceutical company and now in partnership with Eli Lilly, and this was presented by Li Jiang from China and discussed by Masako Nagasaki from Japan. So this was a large randomized phase 3 study, and basically they didn't have any survival outcomes yet, but they had progression-free survival outcomes. So it was essentially standard pemetrexed, carboplatin or cisplat at the investigator's discretion, and stratified for the use of cisplatin or carboplatin, stratified for PD-L1 expression, and stratified by gender. And the population was previously untreated non-squamous, non-small cell lung cancer without an EGFR and ALK1 mutation, good performance score patients. There was no survival data as yet, but the progression-free survival data was clinically meaningful and statistically significant, with a difference of 8.9 months median progression-free survival versus 5 months in the patients who did not receive sintilimab. And there was benefit across all the subpopulations, and there was no major difference by PD-L1 score. So, of course, we need to wait for the survival data to mature, but that didn't reach statistical significance as yet, but clearly a separation of the curves so far for the benefit of the addition to sintilimab. So yet another paper in this space that's suggesting that the use of PD-L1 inhibitors upfront, either on their own or in combination with chemotherapy, may be of benefit in good performance score patients, and that's regardless of the PD-L1 score. So we still have some PBS restrictions around the PD-1 or PD-L1 score, but in fact that may no longer be of clinical relevance. And again, the PBS may need to catch up in some aspects of that. Now, the second paper was a phase 3 randomized study of ensartinib, a new ALK1 inhibitor, versus crizotinib in ALK1 positive non-small cell lung cancer patients, the EXALT-3 study, presented by Leora Horn from the US and discussed by Christine Lovely, also from the US. So this was a large international study, and we even had patients from Albury-Wodonga go on to this study. So it was interesting to see that presented. So this was the first look at that data, and the take-home message in these patients with stage 3 or 4 ALK1 positive non-small cell lung cancer was a clear difference in the progression-free survival, 25.8 months versus 12.7 months. Again, we need to wait a little bit longer for the survival data, but looks like a big difference. Now, to put that in context, we have a number of second-generation ALK1 inhibitors in development globally: ceritinib, ensartinib, entrectinib, and they're all in the early studies look to be clearly better than the standard treatments now, crizotinib and alectinib. So there's more news to come in this space.
So, Craig, soon we have more inhibitors than patients.
Absolutely, Hans, remembering that this is 1 to 2% of all lung cancers, but there's a number of active agents, and it looks like the second generation is going to be even more effective than the first generation drugs. So that was a great paper.
Keep going, Craig, because I'm just at the checkout and they don't take PayPal, Manolo Blahnik.
Yes, Craig, please go to the third abstract.
Hey, Hans,
third.
I have to tell you, you need to learn if you're going to stay on the podcast. Turd is not a good word in English.
So what is a turd? Is it like a turtle then?
Well, this one was from Paul Bus in the Netherlands. So did I pronounce that correctly, Hans? And he presented a paper in mesothelioma. So this is, again, a landmark study, included sites in Australia. Of course, lovely Anna Nowak from Perth was one of the authors. This was a first-line nivolumab and ipilimumab versus chemotherapy in unresectable malignant pleural mesothelioma, to checkmate 743. So, again, standard cisplatin or carbo pemetrexate versus Nivo-Ipi, and it's the low-dose 6-weekly Ipi, which we know from other tumours has less toxicity. And the landmark overall survival data showed an 18-month versus 14-month survival for chemotherapy versus the Nivo-Ipi in favour of the Nivo-Ipi. So what was really interesting in the predefined subset analysis of the epithelioid versus the non-epithelioid mesothelioma, in the non-epithelioid disease, which is a much more poor prognosis disease, there was a substantial difference of 8.8 months for chemo versus 18.8 months for the Nivo-Ipi, which was a hazard ratio of 0.46. So that led on to a discussion about, again, whether we're now getting into subsets of mesothelioma, and the discussant felt that this is now probably the standard of care for the non-epithelioid group. But for the whole population, the interesting question is really whether there needs to be more studies, and whether, in fact, the combination of the checkpoint inhibitors and chemotherapy is the way to go in the future with these patients. So all roads seem to be leading in lung cancer to the combination of chemotherapy and checkpoint inhibitors up front.
Thanks, Craig. And now it's over to you, Hans, for your interview with Giovanni on all things technological. How will cancer in the future be diagnosed? Surely not from our Apple Watch.
So I'm very pleased to have Professor Giovanni Maglia here together with me for a very interesting interview about nanotechnology and cancer. So Professor Giovanni Maglia is actually trained in pharmaceutical chemistry in Bologna, Italy. And then he moved to lots of places. So he came also to Leuven, but he went also to the University of Birmingham, then went back to Leuven. He went to Oxford, back to Leuven. And then now he's in Groningen, where he's also professor and working mainly in the field of nanotechnology. He's actually a good friend of mine. He made a very good decision in his life, so because he married a Belgian. Then he made a very bad decision because he moved to the Netherlands. And he's originally Italian, so he has some difficulties of adapting. And Giovanni, I think you're now fluently Dutch speaking. Am I right?
Well, not really, not at all. That's one thing that is still quite difficult for me, learning your language. So I try to escape, but I went to the Netherlands, same language, no way that I can. Now I need to learn it at some point. It will happen before you die. I will learn some Dutch.
Okay, that sounds perfect. So explain me, what is the main difference of working in the Netherlands versus working in Belgium? Because you did both.
Yeah, so maybe not many people know the difference between the two countries. Being married to a Flemish girl, so I learned it quite quickly, actually. So the Belgians are the last Latin of Europe. So despite they're very close, inner kind of personality is quite Latin, while the Dutch are the first, northern of Europe. And that's a big difference. They speak the same language, but their approach towards everything is diametrically opposite. So the Dutch are very organized. They always kind of think about, 5-10 years in the future. The Flemish, they like more to think about the present and enjoy their life. The Dutch are more kind of Calvinistic in always trying to just be proper and do things in a certain way, while the Flemish are a bit more relaxed in that aspect. So although they speak the same language, although people might disagree about the same language, but basically it's the same language, they are very, very different. And
yeah, indeed.
Yeah,
I fully agree, and especially for an Italian, which has completely different genes, is not always easy. But let's focus now a bit on the topic of today. It's about nanotechnology. For me, this sounds like a term which just means very small, nano, something that you cannot see. But what does it mean, nanotechnology?
Nanotechnology actually is relatively, new in terms of when people actually start actively to study and to learn about it. So indeed, the definition is kind of vague about objects that are between 1 and 100 nanometers. Just to give an example, they're about, a cell is about 1,000 times bigger than that. So, something like that. And so there are objects that are much smaller than cells, basically. And that's actually quite important because the property of objects that are so small, they can differ quite extremely from large objects. So when you study nanotechnology, you kind of need to get into your own world of very small objects that behave in a very, sometimes weird way, very different from larger objects.
Because is it something that you can see? But because there are no, let's say in a microscope, it will not be feasible, I guess. But maybe you use all the time electronic microscopes. So how do you see it?
Yeah, so if you actually want to see that, many scientists don't need to see things to understand them. That's just, it's a strong part of it. But if you really want to see them, which is always, nicer, you need to use special microscopes that actually use special wavelength of lights. So you fire electrons, for example, rather than actually look lights. So you don't really use lights like in a normal microscope, but sort of microscope that's been invented. And those microscopes, in fact, basically kick-started the field of nanotechnology. They work in a fundamental different way. And now we can actually look at very tiny, small objects with those microscopes. So you can actually do it. The real problem is that it's very hard to look at something that is at the same time very small and actually moves. If you see about, life is always moving sometimes very fast. And this process of moving is quite important to understand. And these microscopes are not very good in that. So we need to use different techniques and different kind of approaches to actually look at very small objects that they actually do move. And there are ways to do that as well.
And in the field of cancer, where do you see it? Because if I spontaneously think about nanotechnology, it can be either treatment, like you get some kind of small molecules within the cell, but also like detection. Or where do you see a place of nanotechnology within cancer?
So nanotechnology, basically looking at these small objects, are the kind of objects that are proteins. So if you see a cell, it's quite large, but it's like a bag, right? So it's a bag which is a membrane around, and inside this bag is full of DNAs, proteins, and other kind of objects. And these proteins are actually a few nanometers in size. So like if you actually want to understand these proteins, or you want to detect cells that are gone bad, for example, cancer cells, what is inside the cells actually changes. And most often what changes is, these proteins. The amount of these proteins is different, or actually the quality of this protein is different, or certain aspects of these proteins are different. So like if you actually want to detect cancer early, you need to be able to detect these proteins, which are a few nanometers across, at early stage. At the same time, if you actually want to treat cancer, there are many ways to do that we all know. But like recently, we are trying to understand how we can actually target these cancer cells specifically. And to do that, you need to target specific structures in the cell, which are, again, a few nanometers across. To be able to do that, you actually need to develop the understanding of how these molecules behave and how the interaction between molecule and matter happens at these tiny little scales that we have.
Because screening-wise, I think mainly about like liquid biopsies is something that we speak about a lot in oncology. And when we speak about liquid biopsies, it just means that you take either blood, urine, saliva, whatever, and that we detect for, let's say, mutations based on genetic material, so DNA. So we try to detect DNA.
Right.
But if you want to search for, let's say, early cancers and you think about the nano field, is it then the same detecting of the more, or you're speaking more about detection of proteins that are floating around in the blood?
Yeah, so like today we can really detect anything in the lab. So like if you take a blood sample and you just go to a specialized lab, you're just gonna say, all right, detect this or those molecule, and you can do that. The real challenge though is to actually detect these molecules in real time. For example, if you do an operation and you want to see the variation of certain kind of molecules in blood or anything, or in cancer, if you want to early detect cancer, you would like to have something that you wear that will tell you if you're subject to a certain risk of cancer. At this moment, this kind of sensor do not exist. So, for example, you have your iWatch or whatever other wearable device that you have. It tells you the pressure, it tells you, maybe the temperature of your body, and etc. But it's not able to tell you anything about the composition of your body. So like any chemical that's in your body cannot read. And the reason for that is because we don't have this sensor that are capable of reading these molecules. Because these molecules are very small, right? So like you have this, going from a few nanometers to tens of nanometers is basically the maximum size of this molecule that you want to detect. DNA is a special molecule. You have special techniques to do that. But for everything else is really, and it's also DNA is actually very small. It's a couple of nanometers across the diameter of DNA. So basically, if you want to detect these molecules, and especially if you want to detect it in the background of what you're doing, so let's say you're doing sport or you're just living, and then you have a watch that tells you, all right, so like you're all fine, or no, something's wrong with you, just go to get checked by a doctor. You need to develop this new sensor, which inherently they need to be able to look at very small molecules. And that's what actually our research is mainly focused in, is actually to create this sensor that are able to measure this molecule in real time.
And how do you start a project like that? Because, okay, I can also say I want to make a sensor, but how do you make a sensor? Do you look for specific proteins that bind to other proteins? Is it something universal that you want to bind all the DNA to one sensor or all the proteins to one sensor? Or how do you see this?
Yeah, so like there are two main components in a sensor that if you want to make a sensor for wearable devices. The first component is actually something that is able to bind the molecule of choice and recognize it. So like in blood, you have millions of different proteins that you need to be able to look at that one in particular. So that's the first aspect. And then there are many ways to do that. So like that's actually over the last 50, 100 years, like we really learned how to do that very well. But then there is the second aspect of a sensor, which is that we are very good in making very small electronic devices, but we are not very good to make a very small, mass spectrometer, a very small chromatography device. So that doesn't work. So you can't do that. So these two devices that I mentioned are typically used to measure these molecules in the lab, while electronic devices are typically used in your watch, in your iPad, and etc. So to marry the two is a real huge gap that we have. And we do that by using these very tiny, small holes, which are called nanopores, which are very small proteins that make a very tiny opening in a membrane. And this very small aperture are very good in transducing a biological signal into an electronic signal. So that's the key area that's our research, for example, is focused on. And that's allow us to bridge this gap. So like then you have now, traditionally various techniques that can identify molecules, and then we can transduce this signal into electronic signal. So we can integrate in very small devices. So now I would say that it becomes possible to actually make a diagnosis of illnesses, many sorts of illnesses, very quickly in this manner.
And do you have some inside information where the big companies, I'm thinking of Apple, but also other big companies also have interest in this? Because you speak about the iPhone or whatever, or the iWatch, anything that can sensor it would be really a huge hole in the market, let's say.
Yeah, you're correct. There are many companies that would like to do that. The point is that the technology doesn't exist. So there is a big gap in the technology, and that's what we're working on, to kind of bridge this gap. So you mentioned DNA before. So this technology we're using already works with DNA. So like you can already sequence DNA by passing them through these tiny little pores. But that's the only thing that's possible at the moment. So like people are looking off.
Because if I think of nanopores, there's holes within the cell. So in theory, is it then also not an option to bring molecules that are toxic for cancer cells specifically within these nanopores into the cell? Because sometimes what we have a problem now is with targeted therapy that it either doesn't reach, doesn't bind, doesn't get into the cell. So do you think this is also a strategy we should look at?
Yeah, so like now technology also is actively moving towards that direction. So like you have different ways to do that. So like traditionally people, what they do, they use nanoparticles to try to target cancer cells. Why they use nanoparticles is because, again, they have a certain size that is compatible with the receptor that you have in the cell. So you can actually identify these receptors that are overexpressed in cancer cells. And then you can actually use this nanoparticle to target towards these receptors. What we are doing is something similar, but instead of using nanoparticles, we use nanopores. So like we modify these proteins that they form these pores on biological membranes, and we try to direct them towards cancer cells. That actually works reasonably well. So because indeed these molecules are proteins, and these proteins are also expressed in the cancer cells. So you can actually just cut and paste this molecule to the nanopores and then direct them to the cancerogenic cells. And then at that moment, you can do two things. One, you can just open a hole on the membrane and kill the cell, or you can open a hole in the membranes and actively engineer these pores to import other molecules. It could be DNA, it could be toxic molecules that can kill the cells itself.
So maybe an important question for our listeners, do you think it's something really nearby, all this technology, something for the coming years, or you think we still need 10, 20 years because we will speak more about nanotechnology? So how far are you evolved in this field?
Protein therapy, which is what we in aspects of as well for this nanotechnology and this protein technology, is a reality. So right now, a lot of new drugs come that are protein-based. The difference that has to happen is that instead of having, right now these proteins are mainly antibodies, and they can be used for immunotherapies or just to block a biological aspects of a biological process. So the change in mentality that needs to happen is that you need to use this protein as a more active players to actually introduce other molecules inside the cell. It's difficult to say when it's going to happen because usually these changes, happen very fast. So when people realize the potential, it takes some time for the field to really kind of engage it, and then things will happen extremely fast. But at the same time, if people don't realize it, that pharmaceutical companies or in the labs, then it can actually sit there for a while. So at the moment, the effort is in this antibody therapy, which is exploding at the moment. A bit more focused, functional is a bit more difficult because to introduce this kind of aspects are more challenging. But I'm expecting that soon is going to happen.
To me, it sounds really futuristic, but we thought about this a lot because when we were young, we didn't have computers and see how we do it now. So I think in a couple of years, we will probably see more of this nanotechnology used, and I hope also within the clinic, of course. So I'm very pleased that I was able to interview today, Giovanni. So hope to see you soon because, we're good friends, but actually we never see each other, and especially with Corona, it's becoming more difficult. But he's living now in Groningen, which is quite far also from where I live in Belgium. But we have certainly to see each other maybe again also, or with Zoom or whatever technique that we have now to do it. Thanks, Giovanni. Thanks a lot.
Yeah, thank you very much, Hans. And I'll see you soon, certainly. All right, thank you.
Hans, that was really fascinating. And I'm definitely going to keep an eye on where you're investing. Now, can you give us your quick bites, please?
Yes, I'm very pleased to present today my short bites. So I have selected 4. Must say they're all very interesting, especially the last one. And we can still debate a bit on that one. So keep listening. The first one, it's published in GCO, August 2020. And it's called dabrafenib and trametinib in patients with BRAF V600 mutations. And it's results of the NCI MATCH trial. We know that this combo is active in certain BRAF mutated cancers, such as melanoma, lung, thyroid cancer. I must say in colon cancer is not really active, this combo. But in this trial, they tested more than 16 different tumor types, and it seems that many patients benefit for several months with this combination of a BRAF and MEK inhibitor. So I think it's a good strategy across the majority of BRAF V600 mutated cancers. The second paper I selected is from JAMA Oncology, July 2020, and it's called Adjuvant Systemic Chemo versus Surveillance Following Upfront Resection of Isolated Synchronous Colorectal Peritoneal Metastasis. We know that these patients often get cytoreductive surgery with hyperthermic intraperitoneal chemo, but there are no data from randomized trials to tell us whether we should treat those patients with adjuvant chemotherapy. This study was not a randomized study, but an observational study, but they showed that there was an improved overall survival in the patients that received adjuvant chemo, which were matched with those allocated to surveillance. So I think it's the first data that we have. I think it's something we do in practice already, but now we have some data to support the use of adjuvant chemo in this group of patients. The third paper I want to present, I think is also a very interesting one, published in Lancet, and I'm waiting for this paper already for several years because I used to do some research in the field of Barrett, as you know, is the precursor of esophageal cancer. And the paper is called Cytosponge threefold factor 3 versus usual care to identify Barrett esophagus, a randomized trial. For those that never heard of a cytosponge, it's actually a cool device. It's a small mesh sponge within a soluble gelatin capsule, and it's attached to a thread. So you swallow it with water, it dissolves in the stomach, and it expands into a sponge-like mesh of about 3 centimeters.
Hang on. It's attached to a what?
A thread. A string.
I think that's a thread.
Thread.
Okay, a thread.
A thread.
At least it's not a turd thread.
So, can you still follow, Eva?
When I'm not laughing, I can.
Okay, so when you remove the sponge, it collects cells, and these cells are used for molecular analysis. And what they did is they randomized 13,500 patients to usual care or the cytosponge. And what they found is that in patients with GA reflux, so with gastroesophageal reflux, the cytosponge testing results in improved detection of Barrett esophagus. Of course, they still have to prove whether this also long-term benefits the detection of early cancers or dysplasia. The final abstract I want to discuss here, it's called Industry Payments.
Before you get into that, I just want to go back to that JAMA paper about the adjuvant chemotherapy following resection of the isolated Met. So this is something that we often talk about in our MDT. So were these patients just with one or two Mets? Because you talked about HIPEC. So are these just people with one or two small Mets, or are these people with extensive metastases that have been resected?
The problem is it's such an extensive study in so many centers. It's an observational study, so it depends on the center what kind of criteria they use. They just selected those patients that according. No,
you don't know, do you?
The authors don't describe in detail. It's not a randomized trial where they select a certain group. So it's all the patients that received. So they selected based on this registry.
Sure. Okay. I'll click on the link to get some detail.
There was a little bit of a Twitter discussion after this because the authors and some were portraying this as definitive, but there's a lot of bias in who got what.
Yeah, but that's, as I already explained, there is no randomized data. So I think this trial doesn't give the answer, but it's at least some data that supports the use of adjuvant, or if you can call it adjuvant chemo in this setting, I think.
But Hans, there probably is never going to be a randomized trial, although it's a really important issue, isn't it?
I think it's a common issue, Eva. You know, you have patients who have their surgery for their colon cancer. They think it's fully resected, but in the histology specimen, there's an isolated Met that is found. And then the question is, are these actually fully resected metastatic patients? Should we give them adjuvant treatment or not? So what we tend to do is really try and fit it to the patient. So maybe you'd observe an elderly patient and only treat them on recurrence, but for younger patients, you probably would give the benefit of the doubt and give adjuvant. So is that what you do in your centre?
What I do is indeed, most patients, I would give adjuvant therapy, but of course, depending on the age, comorbidity, complications, post-surgery, etc., we decide not to. But I'm quite pleased because, as Eva said, it's quite difficult to do a randomized trial. So we have to do it with the data that we have. And maybe in the future with liquid biopsies will give us the answer which one needs adjuvant and which will not.
What's your last one, Hans?
So my last one is the most interesting one, and I really want to know your feedback about this. It's about industry payment to Australian medical oncologists and clinical haematologists. It's an analysis of publicly available disclosures. It's published in the Internal Medical Journal, August 2020. So the goal was to analyze the extent of payments from the pharmaceutical industry to Australian cancer physicians. What they did is that during November 2018 to April 2019, so less than a year, they used a file which was downloaded from the Disclosure Australia website, and they found that around $7 million was paid to 2,775 medical practitioners. Of
How
which
much?
$7 million.
Wow.
So of these 2,700, 236 were medical oncologists, so it's 10% of that total. And this 237, this represents about, I think, 30% of all medical oncologists in Australia. So not all medical oncologists get funding or get money from the pharmaceutical industry. The median payment was $2,131, but they concluded that the pharmaceutical industry pays quite some money to specifically medical oncologists. So, Eva, what's your feedback on this? Do you agree with this approach?
I think it needs a whole podcast to itself.
Yeah, I agree.
I mean, it depends what I was asked to do a podcast on COVID and anxiety for oncologists. Now, you can do it after hours for free, but you don't want the pharmaceutical company not having to pay for experts. So I always donate the money straight into my lab fund and use it to fund some researchers going to conferences, etc. I would much rather prefer that the pharmaceutical companies all paid a third party. I do not like direct educational activities.
Is this also registered? Because, if the money goes officially to you, maybe some keep it in their pockets, but maybe some also put it into the lab. So can you discriminate within this file where the money goes to?
No, but it's all publicly recorded and publicly available. So now I'm going to ask you, Hans,
But in Belgium, we have the same system. So I think it would be interesting that I do a study like this. But the problem we have here that it's not obligatory. So I always have to say whether I want it to be public available or not. Of course, more and more industries want us to put it publicly available because otherwise it sounds like a bit sneaky. So I always put it there. But then you sometimes see that I get quite some money from industry, also for advisory boards, etc. And some people get zero income, which is also not possible. So for me, it would be better that it's obligatory for everybody or for nobody. But I think in the future in Belgium, it will become obligatory. And I have no problems with transparency as long as you tell them what it's for.
I think it's a serious topic. I think it depends on what people are getting paid for.
Yes, but I'd rather education be at arm's length. So that segues nicely into me asking Rachel, can we get paid to do this podcast?
Yes, please.
We just want to say we don't have any sponsorship at all. What were the author's conclusions, though, Hans? Were they for it, against it, or didn't really comment?
I already told you for my short bias, I didn't read all those papers into detail because I didn't expect any questions.
So maybe listeners, if you do want us to have a debate on this topic, contact us through Twitter or through Oncology News, and we can do a whole episode and make Hans read the entire paper. We can certainly interview Adrian Picorni. He was one of my registrars a long time ago. If you think it's an interesting topic, let us know. But now it's on to
PBS update. So Eva, just to let people know that olaparib is now on the PBS for both somatic and germline BRCA-mutated patients in second-line maintenance of platinum-sensitive relapsed high-grade ovarian cancer. So that's more than 2 prior courses of platinum-based regimens. So, and interestingly, this has been a real problem in Australia in the past. They actually approved the MBS item number to do the tumour BRCA testing at the same time as the PBS listing. So in the past, we've had PBS drugs, but there's no reimbursement for the test. So hooray, there's now actually been some coordination, and both the MBS item number for the testing and the PBS item number for the drug were approved.
Thanks, Craig. Good news. And I've got some news now from the investor update. So reading the financial papers or Twitter, there was a positive result from 2 trials of first-line IO in gastric, esophageal and GE junction cancer, and also adjuvant nivolumab improved disease-free survival in resected gastric and GE junction cancer. But there was another very interesting announcement in the financial news that adding atezolizumab to chemotherapy did not improve PFS in first-line PD-L1 positive triple-negative breast cancer. So a lot of debate about why this particular IO has not shown the results of previous IOs, and we await the scientific announcement, not just the investor update.
Thanks, Eva.
So it's been another fun podcast, interesting, controversial, bit of shopping. Thank you very much to my wonderful co-host, Hans Prenen.
Thank you, Eva. It was a pleasure as usual.
And to the lovely Craig Underhill.
Thank you, Eva.
If you want to read more about Craig, subscribe to the Border Mail. He's making great headway trying to move the New South Wales-Victorian border. Thanks to you too, Rach. See you next time for the next podcast, Oncology Journal Club. Bye for now.
You've been listening to the Oncology Podcast. If you enjoyed today's edition and would like to subscribe, head over to our website, oncologynews.com.au, and sign up to our newsletter. Thanks for listening.